All right, so example 6. It says simplify the following trig expressions to a power of a single trig function. So kind of some vague instructions there. Simplify, we get that to a power of a single trig function. So what that means is in the end, we want it to be like some trig function to the nth power of x. So like sine squared of x could be an answer, or just cosine of x, because that would be the first power, or secant to the 5th of x, you know, that's our goal. So we don't know what the power is. We don't know what the trig function is, but we know it should be one handsome little dude at the end, okay? Now, we are starting with expressions. This is a mathematical expression, of course, so we're going to work straight down. We're not even going to put equal signs, but every line has to be equivalent to the line above and below it. So what are we allowed to do with expressions without changing their value? Well, some of the rules of algebra tell us we can what? We can combine like terms, and we can combine like factors. We can do that. We can expand something out, like distribute if we want to, if it's factored. If it's expanded, we can go the other direction. We can factor it. That works. What else can we do? We could divide out common factors. We can cancel opposite terms. What else? Oh, we can get common denominators to combine two terms into one. We can split up numerators to break it into other terms. And then in terms of like creating something, we can multiply by a clever form of 1, right? Which is kind of what we do when we get common denominators. And we can also cleverly add a 0, which would be like completing the square. And that's about it algebraically. But we also have these new tools called identities, which are mathematical synonyms, right? And so what we could do also is replace one expression with something else that it's equal to, like wow with holy cow. They're equivalent expressions, but not in a trig sense, right? Or any combination of those two things. Algebra, identity substitution. In any order, in any sequence, step by step, all the way down until we get it down to a single power of a trig function. Now, as we do that along the way, the steps themselves become the product. So the process becomes the product. So you want to make sure you meticulously show every single step. And if there is a doubt whether to include it or not include it, when in doubt, do not leave it out. Okay, so that's what we're going to do on part A. But as I'm standing here, I see these retests. So you can retest anytime until Friday at 4:20. I'll be here every morning and every afternoon the rest of the week, except Friday afternoon. So if you haven't done so already, make sure you do that. You could also do it during another class, advisory, whatever. 7th period, I'm off, but anytime. And I'm still working through the giant pile. If you've already done it and it's not in the grade book yet, I've just been kind of like doing so many reviews before and after school. I've been going home tired and haven't gotten to yet. But it is the last 9 weeks, and I will get them in before June 12th. I promise. Woohoo, right? Yeah, no, I'll get them in. The last day of school is May 26th. Okay, wow, 16 days. So I'll get them done. Have no fear. I will get them done. Okay, you ready? Here we go. Part A. What's the net? What do we put underneath there? What goes next? Well, I'll be talking to you through some strategies, but they're only strategies. It's not going to be like do this every time, right? You have two terms, right? Something plus something. We need to eventually get two terms into one term. Two terms into one term. If one of those were a fraction, at least one, we can combine them by getting a common denominator, but they're both over 1 right now, so that's not going to help. Sine, sine, cosine. Cosine seems out of place, doesn't it? What if I were able to put everything in terms of sine? That might be a good place to start, right? So that's what you tell yourself. Can I get the cosine squared of x in terms of sine? And you think about identities for getting that done. Do we have any that allow us to write cosine in terms of sine or cosine squared in terms of sine squared? Yeah, there's actually two different options. Okay, so off to the side, this is what you're thinking. Whoa, off to the side. Or this could be in your head what you're thinking. The first way that I could do that is I could write cosine of x using the co-function identity as sine of pi halves minus x. That would change it in terms of sine, but there's a problem with that. See, the problem with that is I have an angle of x, and if I change it to sine of pi halves minus x, now I'm changing the angle in that one only to pi halves minus x, and that's not good. If your angles are different, then you're not going to be able to combine them together. They're completely different species, right? It's like trying to mate a hippo with a yo-yo, right? Two different species. A yo-yo, that's not even an animal, right? It's not going to work, right? What's the point? So I don't want to do that. In fact, if you ever start and your angles are different, your primary objective is to get the angles the same first. Turn that yo-yo into a hippo and then leave the hippos unattended, okay? All right, that's your first goal. So I don't want to do that. So, hey, because cosine is squared, and this is where knowing your identities is important, is there a way to relate cosine squared to sine squared? Yes. So let's review Papa Pid, right? Cosine squared of x plus sine squared of x equals 1. Now, sometimes that shows up by itself like that, but more often than not, we use different versions of that. So now that we know it's an identity, I can actually like bring the sine squared across and say cosine squared is 1 minus sine squared. That's a version of Papa Pid, okay? Or similarly, if you bring the cosine squared across, you get sine squared is 1 minus cosine squared. So I don't know if you want to memorize those versions of it, but just be aware of that, okay? If you do your due diligence and you do your homework, that'll show up often enough that you'll have them without having to sit down and memorize them. I think that's going to be good because what that'll accomplish, if I use the first one, cosine squared becomes sine squared, but more importantly, the angle x stays the same. See that? So that's good. So let's go ahead and do that. Now, whenever you do a trig substitution, I would recommend putting parentheses first, especially when you're doing something like this, because we're about to replace cosine squared of x, which is one term, with a two-term dude, right? And that's a whole extra term. So working straight down, we get sine cubed of x, won't do anything with it, plus sine of x, won't do anything with it, and then times 1 minus sine squared of x. Okay, boom, got it, straight down. Yeah, we're on our way. We're on our way. So at least now it's in terms of sine completely. And now what? We just did a trig substitution. Is it time for another trig substitution? Well, maybe. Take inventory, reassess. Remember, you also have algebra at your disposal. Is there anything obvious now that we could do on this line that we couldn't before? Or the opposite of that, the distribute. Is that what you meant? Oh, you meant to factor. Oh, we'll come back to that. Because if I'm going to do that, I'm actually going to do that first. I'll do that as a second way. But what I was looking for, and there's really no wrong way. You could actually factor at this step as well. But because I've created two terms and I have something in front, I can now distribute to both terms. Okay. So let's see what that looks like. Sine cubed is still there, plus sine of x times 1 is sine of x, minus sine of x times sine squared is sine cubed of x. So some obvious math would be to distribute, right? Or factor, which we'll come back to. And now, is there anything? Now you might go, oh, you get excited. Because you got a sine cubed and a negative sine cubed. And those what? Those divide out. No, they don't. They what? They cancel. And so you get 0 plus sine of x, and then 0 plus anything is itself. Now, do you really need to put 0 plus sine of x? I probably wouldn't count off if you just went straight from there to sine of x. But in general, if there's a reason for something to happen, you would want to show it. So like the reason to go from here to the second to last line would be cancellation, right? And then from here to sine of x would be identity element of addition, right? But it's almost so trivial of a step. If you just went straight from here to here, I wouldn't count off. But again, when in doubt, should I show it or not? Don't leave it out. When in doubt, don't leave it out. And there you go. Sine of x is sine to the first of x. That's a single power of a single trig function. And so that's it. That's the answer. Okay. Now, when we start doing trig proofs in earnest, it's actually going to be a little bit easier, not just because you're going to have more experience, but you're going to have a definitive target. I'll actually set that equal to sine of x and have you prove it instead of simplify. And now you have a definitive target. Not only do I want it to be a single power or a single trig function, but I want it to be sine to the first of x. Okay. And the method would be very, very similar. Okay. So is that the only way to do it? No, no. Let's look at another way here. Some options, just because they're kind of nuanced. Let's rewrite it. Sine cubed of x plus sine of x times cosine squared. Now, Misha had an idea that she said to factor, right? So we could actually do that from the very beginning. Someone else might say, I'm not trying to get it all in terms of sine and cosine. Someone else might look at it and say, I spy 2 terms, and there is a common factor in each of them of sine of x. And so another way we can take 2 terms and turn it into 1, aside from a common denominator, is if I could factor it. And so if I factor out a sine of x from both of them, which we could have done on the second line up there after we replaced it, but it's probably a little bit easier if we would have done that from the beginning had we recognized that. So what do I get when I factor out a sine of x from a sine cubed? Sine squared, right? Is dividing out. And then if I take the only sine of x out of the second term, I'm just left with cosine squared. So there you go. Factor out common factor. And now we look at that. And if you wanted to call cosine squared 1 minus sine squared, you could, but I don't think you really need to, because what are we staring at now inside the parentheses? Papa Pig, right? Sine squared plus cosine squared is the same as cosine squared plus sine squared. So that's equal to what? 1. So again, I'm going to show that. That's sine of x times 1, Papa Pig. And on the next line, anything times 1 is itself, identity element of multiplication. Okay. So I don't know which way is correct. They're both correct, right? The bottom requires 1 fewer lines of writing. And so typically, if there's more than one way to do it, we tend to favor the one that's the most economical, the most efficient, because it's fewer steps, less likelihood of making a mistake. And some people would even say it's more beautiful. All right, are there other ways to do that? Yeah, but they're probably more extravagant, more scenic, right? These are the 2 most direct routes. And there you go. If it's not fun easy yet, it should be at least fun. But the ease will come with more practice, okay? Notice I didn't go into their definitions in terms of X, Y, and R. We don't do that anymore. We only did that when we were trying to prove the fundamentals. Now we're using the fundamentals themselves to simplify or later to prove bigger and better things. Okay, comments or questions on that one? So far, so good. 1 down, 5 to go. 1 down, 5 to go. Letter B. Secant of x minus 1, secant of x plus 1. Do your math homework. It's due Monday at 9. Okay. Secant x minus 1, secant x plus 1. Whoa. Well, what can we do? Well, one thing you could do is say, you know what? I'm not a fan of secant. I like this one over here because it was in terms of sine and cosine. So one thing that you could always do at any time is to write everything, if it's not already, in terms of sine and cosine. And that's possible because that's how we could get the other four trig functions from the unit circle, by just knowing cosine and sine, right? Secant is 1 over cosine, cosecant is 1 over sine, tangent sine over cosine, and cotangent is cosine over sine. So if you wanted to, you could call that 1 over cosine minus 1 times 1 over cosine plus 1. But I would hold off on that. I wouldn't let that be your first strategy. That's a good strategy when it's necessary, or when you absolutely have no idea what to do next. It could be kind of like your get unstuck by putting everything in terms of sine and cosine. And I know some of you are saying, oh, but sir, I'm stuck already. I don't know what to do. So, okay, well then do it. Do it. But I would recommend something else. Anyone have a recommendation? Is there any obvious math to do? Quote unquote obvious. It's only obvious if you see it, but multiply it out. Multiply it out. Yeah, foil it, right? Expand it. And that should actually be even a stronger feeling, because secant x minus 1 and secant x plus 1 are what's of each other? When the only difference is the middle sign, x plus 4, x minus 4. It rhymes with ronjugates. Conjugates. Excellent. Excellent. These are conjugates of each other. And we know that if we multiply out conjugates, the middle terms cancel, and we end up with a difference of two, not circles, but squares. Yeah. So let's go ahead and multiply it out. You don't have to show the inner and outer term. You know they're going to cancel. So secant times secant is secant squared, minus secant plus secant, they cancel. And then -1 times 1 is -1. So we get secant squared minus 1. All right. Now what? Erase the -1 and be done? That'd be secant squared. No, no. Here's what you should be thinking at this point, right? And you can do it anytime. If you ever have a trig function that's squared, like we did over there with cosine squared, anytime you have a squared trig function, you can use the Pythagorean identity. It's an option. But if you ever have a squared trig function, comma, especially in the presence of another term that's a 1 or -1, then you should really be thinking Pythagorean identities, because they all have squared trig functions and the number 1 in it. So secant squared, was there a PID with secant squared in it? And the answer is yes. So if you don't remember, go off to the side and remember, we learned it like this: 1 plus tangent squared is secant squared. So that's where you got to have them memorized. Now there's two ways you could do this. Let's go down this fork over here. We'll call this method 1. You could say, I'm just going to replace secant squared with what it's equal to by baby PID number 1. Secant squared is 1 plus tangent squared. And then I'll bring down the -1. And now, is there any obvious math to do here? 1 take away 1 is 0. So you get 0 plus tangent squared. And then that's just tangent squared. And that's a good place to stop right there. Single power, single trig function. But you can be more efficient if you want to. Just like I said up here, you're allowed to just call cosine squared 1 minus sine squared. You can look at different versions of this. And with enough experience, it'll become second nature. You're like, secant squared minus 1. Why, if I just bring that 1 across, I get secant squared minus 1. And that immediately then will equal tangent squared. So different versions of the same trig function or the same identity are allowable. Secant squared minus 1 is tangent squared. And now you're done in 2 lines. But if not, you just got 2 more lines to go. No big deal. It's like you go around the plaza, you meant to go halfway around, but there was a car there, a jerk didn't let you over. So you just go around 1 more full time and then get over, or attempt to get over, right? If you've seen European Vacation, sometimes it could be hard to get over. Is that the only way to do it? No. Let's look at that fella that said, hey, I'm stuck from the beginning. I like that strategy of putting everything in terms of sine and cosine. So that would look like this: 1 over cosine minus 1, and 1 over cosine plus 1. Okay. Now, you could FOIL it out from here, but now you're foiling fractions. So here's another kind of approach. I want it to end up being a single term. Right now I have 2 factors, and in each factor I have 2 terms. In order to get 2 terms into one term, we need a common denominator. So if at least one of them is a fraction, you can do that. So what I'm going to do is I'm going to replace 1 in both of those with cosine x over cosine x, okay, getting a common denominator. So this becomes 1 over cosine of x minus cosine x over cosine x times 1 over cosine x plus cosine x over cosine x, multiplying by a clever form of 1. All right, and now, since I have a common denominator in the first factor, I can put it all over cosine x, and then the top becomes 1 minus cosine x. In the second factor, I get 1 plus cosine x over cosine of x. Well, now I'm multiplying something times something. So I can multiply straight across. 1 minus cosine times 1 plus cosine. And then the bottom, I can do cosine times cosine. So now I can go ahead and get rid of all the parentheses. Let's do the bottom first. Cosine times cosine is cosine squared. And what do you notice about the top? How are 1 minus cosine and 1 plus cosine related? Rhymes with conjugates. Ronjugates, yeah. Conjugates, yeah. Can a word rhyme with itself? Yeah, it's kind of, yeah, I guess it can. So ronjugates, right. So this is 1 minus cosine squared. And now you're like, ooh. Maybe. Do those divide out, those cosine squareds? Yeah. No, they don't. It's a term in the top. So you can either split up the terms in the top over the bottom, 1 over cosine squared minus cosine squared over cosine squared, or you can say, what's another name for 1 minus cosine squared? Sine squared, yeah, a la Papa Pid. So that's sine squared of x all over cosine squared. And now you're like, okay, by the ratio identity, sine squared over cosine squared is tangent squared. And we got the same answer. Okay, now that's a lot more scenic. That's like trying to get off the plaza, but now you go around like 57 more times before you get out, right? That's the extra fun. You do it on a Sunday when there's really nothing better to do, just because you're crazy. All right. And are there other ways to do that? I'm sure. I'm totally sure. Yeah. So as long as you get the right answer, that's all I'm going to require you to do. I'm not going to require you to do it in the X number of steps, right? Whatever it takes you, so long as your notation is good, right? We work straight down, no equal signs needed, and every line is equivalent to the line above and below. Okay. Comments, questions? Quips, quotes, concerns? Concerns? Yeah, you're right. We probably should have gotten permission slips, right? Yeah. Oof. Yeah, let's see there. All kinds of stuff going on there, right? But what's the first thing that I would probably take notice of? I got a theta, and a negative theta. Ooh, remember what we said about yo-yos and hippos? You got to get your angles the same first and foremost. That's goal number 1. If they're not already the same, goal 1. Let's see, goal 1 is to get your angles the same. Hey, before you even do anything else. So we have 3 options here. We can either get all the angles in terms of theta, all the angles in terms of negative theta, or we can get all the angles in terms of some third-party angle. What would be the easiest, which would make most sense? Third party? Yeah. 3 of the 4 are theta, right? Yeah, let's just stick with theta. That way we only got to worry about changing this guy. All right. So is secant, let's see, the even odd identities, right? Is secant even or odd? Even. So what do? Do we bring the negative out front or forget about it? Forget about it. We just drop it, right? So I'm just going to bring down that little term. That's just secant of theta. Okay, sweet. Now, I also have something to do with these fractions here. I have 2 terms that aren't fractions and 2 terms that are fractions. Do I want to get rid of the fractions or turn the other 2 into fractions? I think I'd like to get rid of the fractions. At least try that first, right? So as I'm writing down on the next line, I might as well do a little bit in the other terms so that I'm not just doing one crazy line after another. So 1 over cosine is the same as secant of theta. And then we'll leave that as -1. Cosine squared looks good. Cosine squared of theta. And then 1 over cosecant squared, well, that's the same as what? The reciprocal of cosecant is sine. And there's 2 of them, so it's sine squared. Whoa, there's a desk there. Yep. Okay, so we did a couple things, right? We got the angles the same, and then we got rid of the fractions. Just an option. And then we reassess. The first one, secant theta -1, looks kind of like what we had in the previous problem, except with the theta instead of x. The second one also has a secant of theta in it. But now it's got that cosine squared plus sine squared. It's got that cosine squared plus sine squared. Cosine squared plus sine squared. Man, if that cosine squared plus sine squared were gone, that'd be better. If only. Hey, what is cosine squared plus sine squared? It's 1. Yeah. It doesn't have to be written side by side in order to call it 1. The associative property of addition says you can call it 1 if it's written in any order. So on the next line, I'm going to replace the 2 highlighted pieces with the number 1. So that's 1. And then plus secant of theta. Wow. You can remodel that. You don't need a space. And then I'll bring this one down. And now I'm kind of having a little bit of deja vu. And you should too. It's not because I've done this 3 other times today. It's because we just did part B, didn't we? Let's compare it. We're using theta instead of x, but aside from that, look, secant of x -1, secant of x plus 1. We have secant of x -1, and can I flip those around? Heck yeah, because addition is whatative? Additive? It's the additive property of, or the commutative property of addition. Yeah, it is additive. Yeah, no, it's additive. You can add them in any order. How about that? You can add them in either order. So if you flip it around, now it looks pretty much exactly like the start of part B, except for a theta. So all we got to do is say, yeah, see part B, boss. No. All we got to do is maybe just, we have 3 different versions on part B. We can go down the left fork, we can go down the right fork, or we could be the guy that gets trapped on the inside lane of the plaza and rewrite all that. You want to do all that? I don't either. That's a lot of writing. So in the effort of being efficient, let's just go down this fork here. Okay, so we'll multiply it out and we get secant squared of theta -1. And then using baby PID number 1, that's equal to tangent squared of theta. Nice. Wow. So it wasn't that bad, right? The hardest part for some people about doing a problem like that is resisting the urge to complain, right? And there went half your energy right there. Just little by little, right? Got to do something. there another way to do it? You want to do it another way? I don't want to do it another way. That was good enough, right? Yeah. Leave well enough alone. Don't poke a sleeping bear, especially if you just put him to sleep with a lullaby, right? You know how cranky bears can be put down. They don't like nap time. Don't put him to sleep and then poke him. Mixed metaphor. Okay. A, B, C, D comes next. 3 down, 3 to go. We're halfway through with class. And we're not even halfway through with time. So maybe we'll have time for some more problems at the end. I hope. Get your money's worth. You try D on your own. Ready? On your mark, get set, go. You try D on your own. You have some experience now. 1 minus sine squared. Hey, whenever you got a squared trig function, especially, I like that way, especially in the presence of a number 1, you should think possibly the PIDs. And the top one is a version of Papa PID. 1 minus sine squared is cosine squared. Now, the bottom also has a squared trig function and a number 1. So in the same line, you could also do something with that. Now, cosecant squared minus 1, I'm not going to write it, but you can manipulate it the same way we did secant squared minus 1. It's cotangent squared. So some of y'all had that. I saw that. Well, now you get excited because you realize that the C's divide out and the O's divide out and the squareds divide out and the X's divide out, right? And you're left with S over T. Sweet T. But that's not how math works, right? But it sure makes for a hilarious joke. Ha ha. Well, when in doubt as to whether a quotient of 2 trig functions or a product of 2 trig functions simplifies down to something nicer, and it's not already in terms of sine and cosine, this would be now a good time to put it in terms of sine and cosine. So the top is already, of course, in terms of cosine. Main division bar, using the ratio identity, cotangent squared is cosine squared over sine squared, okay? And now you've created a complex fraction, and you should get excited because anytime you create a complex fraction, you don't got to think about what the next step is, because the next step is always get rid of the complex fraction. And you could use state change flip here because the bottom is a single fraction. So stay, change, flip, right? And now you might want to come back and put the cosine squared over 1. Oh, yeah. And now that it's multiplied from high to low, cosine squareds divide out, and you're left with just sine squared divided by 1, which is sine squared of x. And that's it. That's a single power of a single trig function. So that's the answer. Now, that one required 2 Pythagorean identities, right? One on the top and one on the bottom. What if I told you that you could do this problem without lifting a single Pythagorean identity? Yeah, you wouldn't believe me, but I'm going to show you, right? And, there we go. Carson actually was trying this way out, right? You know, and that's just, you know, that's just the wisdom of being a senior, which I now know he is, right? Yeah. So you might be like, you know what? I'm stuck right away, Mr. Corpy. It's not in terms of sine and cosine, so I'm going to put it in terms of sine and cosine right away. So that's 1 minus sine squared of x all over. Cosecant squared is 1 over sine squared of x, and then you get minus 1, okay? So that did use the reciprocal identity. Now we have a complex fraction, but unfortunately, state change flip does not work in this case because there's 2 terms in the denominator. It's not a single term. So you can either A, get a common denominator in the denominator and then state change flip, 2 steps. Or you can use the method that always works, even when state change flip does, the method that we use in calculus, which we've already learned this year. Lick them over, lick them. Remember that? Of course you do. LCM over LCM. of your miniature denominators. But we only have one miniature denominator, it's sine squared. So on the same line, you could just multiply by a clever form of 1, sine squared of x over sine squared of x. Now in the top, don't distribute the sine squared to 1 minus sine squared. Just write it as 1 minus sine squared times the sine squared. Because if you did distribute, you're going to be building up the power to sine to the 4th. And you might realize right away that that's kind of taking you a little bit further away from where you want to go. But in the bottom, if we distribute, sine squared times 1 over sine squared is 1. And sine squared times 1 is sine squared. And now OMG, right? You have 1 minus sine squared factor in the top. You got a 1 minus sine squared in the bottom. Do they divide out? They do. Now, as it sits, you don't need parentheses around the denominator because there's not another factor down there. But if you were to divide them out like that, you would need to add parentheses around it to show that you've divided out the entire quantity. All right, now you're left with sine squared over 1, which is just sine squared. So there you go. We get the same answer. It's actually in fewer lines, so this way is actually more efficient. But they're both correct. They're both correct. One little reciprocal identity and good old lick 'em over lick 'em is all we needed to lick that problem. Is there another way to do it? I'm sure there is. Sure there is. All right. 4 down, 2 to go. Two left. Letter E. Let's see. I'm stuck. Put it in terms of sine and cosine. Crap, it already is. Okay. Let's see. Panic. No, that's last resort. Okay, I'm out of ideas. Hey, look. I spy a denominator of 1 minus sine. Isn't that just cosine by the Pythagorean identity? Yeah. No, because the P in Pythagorean stands for Pythagorean. I gave it away, sorry. They have to be what in order for the Pythagorean to work? Squared. Got to be squared, not cubed, not to the first. They got to be squared. It's not squared. Well, can we just square it? No, that didn't work. But look, hey, I memorized my identities, sir, right? Sine over cosine, that's tangent. So can I call that second term minus tangent of x? Is that legal? Totally legal. Totally legal. But is it going to take me where I want to go? Well, if I do that, I'm going to have to try and write this in terms of tangent. And that's going to be harder because I have 2 terms in the denominator. I can't split it up. So I'd already be kind of at a loss to how to do that. So it doesn't really help. In fact, if it were tangent to start with, I would probably write it as sine over cosine. So sometimes, even though it's legal, it doesn't really help. So here's another strategy that we've already mentioned. I need to get it down to a single term, right? I have 2 terms. At least one of them is a fraction. What do we need to combine fractions? We need a common denominator. Yeah. And to get a common denominator, you can either do crisscross applesauce, butterfly, multiply, or you can actually do it the right way. The common denominator is going to be the product of those 2 guys. So you can multiply the first one by cosine x over cosine x. So that's a clever form of 1 times the existing factor, and then minus the existing sine x over cosine x. And then you multiply that guy by 1 minus sine of x over 1 minus sine of x. So that's the correct way to do it, right? We're just multiplying both of them by a clever form of 1. Whatever we need to get the denominators the same, in common. All right. Now that we know that we are going to have a common denominator, let's go ahead and put a single fraction bar. And I'll do the denominator first. It's going to be cosine of x times 1 minus sine of x. And then in the top, I'm going to have cosine times cosine, which is cosine squared. And then look at this. I got minus sine times the quantity 1 minus sine of x. So don't distribute necessarily in that line. Just take inventory, put it as a single fraction. All right. Hey, do these divide out now? It's a factor in the bottom. It's part of a term in the top. No. If you want to divide those out, divide them out up here, right? But then what's the point of bringing them in? So here's the thing. I can either distribute the cosine in the bottom or distribute the negative sign in the top, or neither of those, or just one of those. Do you want to distribute the cosine in the bottom? Well, what would be the criteria for knowing to do that? Well, you just try it and see if it works. But remember, if we have a single fraction and we're trying to simplify it, we can only divide out common factors, right? All right. It was. This is already completely factored, right? We don't want to expand that out if it's already completely factored. So, nope, I'm not going to do it there. But notice in the top, it's partially factored. The second term is factored, the first one's not. So in the numerator, I do want to completely expand it out, collect like terms, and see if I can factor that one. So let's go ahead and distribute that. So I get cosine squared. And remember, I'm distributing not just a sine of x, but a negative sine of x. It's going to give you negative sine of x and then a positive sine squared of x. And in the bottom, it's just cosine x times 1 minus sine. Okay, now we reassess. God, what to do? Put it in terms of sine and cosine. Already is. Okay. Panic? Already did. Pray? I haven't tried that. Maybe? Divine inspiration? No. What do you see in the top? Yeah, cosine squared plus sine squared. There he is again. Let's pop a pid in the house. So that's 1, and then minus the sine of x that's up there. All over cosine x times the quantity 1 minus sine of x. Did you just hear an echo? Did you just hear an echo? Did you just hear an echo? I said 1 minus sine of x when I read the top. I just said that when I read the top. No, I said 1 minus sine of x when I read the top, and I said 1 minus sine of x when I read the bottom. There was no echo. I was just reading the problem. But because I said that twice, that means that there's a common factor of 1 minus sine of x, both top and bottom. So they divide out, right? Just like that, or must I add something? I have to put parentheses, right? Now, be careful. When you divide that out, are we just left with cosine of x? No, we're left with 1 over cosine x, which is secant of x. Secant of x. Are we running out of time? 1 minute. Oh my gosh. We must have had more fun in here because it went by so fast. We finished part F in every other class except y'all. How does that happen? We just have so much. We have good discussions, I guess. All right. Well, we'll pick up here tomorrow with part E. And I'll go ahead and film your class again. Y'all are a great crowd. Y'all have a great day. Enjoy the rest of your day. Yes.